On Christmas Day 2021, humanity launched the most expensive scientific instrument ever built into space. $10 billion. 25 years of development. Thousands of engineers across 14 countries. A mirror 6.5 meters wide, coated in gold, folded like origami inside a rocket and sent to a point in space 1.5 million kilometers from Earth. The James Webb Space Telescope was designed to see further back in time than any instrument in human history. It was built to observe the first galaxies that formed after the Big Bang, to analyze the atmospheres of planets orbiting distant stars, to answer questions that had haunted astronomy for decades. Scientists knew what they expected to find. They had models. They had predictions. They had simulations run on supercomputers that mapped the evolution of the universe from its earliest moments to the present day. Those models were the product of 30 years of refinement, tested against every observation available, confirmed by satellite after satellite, validated by measurement after measurement. The models were solid. The models were trusted. The models were wrong. When James Webb opened its golden eyes and looked at the universe for the first time, what it saw did not match any prediction. Not partially. Not approximately. The observations contradicted the models so fundamentally that entire research teams went quiet. Papers were delayed. Press conferences were postponed. Scientists who had spent their careers building the theoretical framework of modern cosmology found themselves staring at data that should not exist. And 4 years later, the crisis has not been resolved. It has deepened. What the James Webb Space Telescope found at the edge of the observable universe has shaken the foundations of our understanding of reality itself. If you want to know what made NASA go silent and why the most powerful telescope ever built is rewriting everything we thought we knew about the cosmos, hit that like button and subscribe right now. This discovery changes everything. Let's begin. To understand why the James Webb Space Telescope's discoveries are so disturbing, you first need to understand what scientists expected to find and why those expectations were so deeply held. Because the predictions were not guesses. They were the output of the most successful theoretical framework in the history of cosmology, a model that had passed every observational test for 3 decades and had become the foundation upon which the entire field of modern cosmology was built. The Standard Model of Cosmology, known as Lambda-CDM, describes the universe as composed of 3 primary ingredients. Ordinary matter, the atoms that make up stars, planets, and human beings, constitutes approximately 5% of the total energy content of the universe. Dark matter, a mysterious substance that exerts gravitational influence but does not interact with light, makes up approximately 27%. And dark energy, an even more mysterious force that drives the accelerating expansion of space, accounts for the remaining 68%. This model, calibrated against precise measurements of the cosmic microwave background radiation by satellites like COBE, WMAP, and Planck, predicts how the universe evolved from a hot, dense, uniform state approximately 13.8 billion years ago into the complex web of galaxies and galaxy clusters we observe today. The Lambda-CDM model is extraordinarily specific about the early universe. It predicts that the first stars ignited approximately 100 to 200 million years after the Big Bang, forming from clouds of primordial hydrogen and helium that slowly collapsed under their own gravity. These first stars were massive, hot, and short-lived, burning through their fuel in just a few million years before exploding as supernovae. The debris from these explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, the building blocks of rocky planets and eventually life. Gradually, over hundreds of millions of years, this enriched gas coalesced into the first small galaxies. These early galaxies were predicted to be tiny, irregular, and faint. They were not expected to contain many stars. They were not expected to be well organized. They were not expected to have spiral structure or dense central bulges or any of the features that characterize the large, mature galaxies we see in the nearby universe. Building a galaxy the size of the Milky Way, with its hundreds of billions of stars and elegant spiral arms, was supposed to take billions of years of mergers, accretion, and gradual growth. The early universe was supposed to be simple, sparse, and dark. The James Webb Space Telescope was designed to test these predictions by observing the actual universe during this formative period. Its infrared instruments could detect light from galaxies so distant that the expansion of space had stretched their radiation from visible wavelengths into infrared, making them invisible to optical telescopes like Hubble but perfectly suited for Webb's gold-plated mirrors and cryogenically cooled detectors. Webb would look back in time and see the early universe as it actually was, not as models predicted it should be. Within months of beginning scientific operations in mid-2022, Webb delivered its first shock. The telescope identified galaxies at extreme distances, corresponding to times when the universe was only 300 to 500 million years old, that were far larger, far brighter, far more massive, and far more structurally organized than any model predicted. These were not the tiny, faint, irregular protogalaxies that Lambda-CDM demanded. They were substantial, well-formed galaxies containing billions of stars, organized into recognizable structures, producing stars at rates that should have been physically impossible given the time available since the Big Bang. The initial reaction in the astronomical community was cautious skepticism. Perhaps the distance measurements were wrong. Perhaps the galaxies were closer than they appeared, making them seem abnormally massive for their supposed age. Perhaps calibration errors in Webb's instruments were producing artificial brightness measurements. These concerns were legitimate and scientifically appropriate. Extraordinary claims require extraordinary evidence, and the claim that galaxies existed in the early universe that should not have been able to form was certainly extraordinary. But as months turned into years, the evidence accumulated. Spectroscopic follow-up observations confirmed the distances. The galaxies were genuinely ancient. They existed when the universe was genuinely young. And they were genuinely massive, containing stellar populations that should not have had time to assemble. By 2025 and into 2026, the JWST Advanced Deep Extragalactic Survey and other deep observation programs had cataloged thousands of galaxies in the high-redshift universe, building statistical samples large enough to establish that the anomalies were not flukes. They were not outliers. They were a population. A population of galaxies that the standard model of cosmology said should not exist. The most extreme example discovered to date is a galaxy designated MOM Z14. This object was confirmed in January 2026 as the most distant galaxy ever observed. It emitted the light that Webb captured just 280 million years after the Big Bang. 280 million years. The universe itself is 13.8 billion years old. MOM Z14 existed when the cosmos was barely 2% of its current age. At that time, according to standard models, the universe should have contained at most small, diffuse collections of stars beginning the slow process of assembling into protogalaxies. Instead, MOM Z14 appears remarkably luminous and compact, with characteristics suggesting it had already formed a substantial stellar population in a period of time that models consider insufficient for such development. The lead author of the study confirming MOM Z14's distance described the finding in terms that captured the community's astonishment. The researchers noted that Webb was revealing a universe that looked nothing like what had been predicted, describing this as both challenging and exciting. The study documented that Webb had uncovered more bright ancient galaxies than scientists expected, raising fundamental questions about galaxy formation in the first 500 million years after the Big Bang. The researchers suggested that previously unimaginable distances, approaching the era of the very first stars, no longer seemed far away. But MOM Z14 was just one piece of a much larger puzzle. As Webb continued to observe the early universe, it uncovered a series of phenomena that, taken together, created what many astronomers began describing as a genuine crisis in early universe cosmology. The first category of anomalous objects became known as blue monsters. These are ultra-compact yet extraordinarily bright galaxies found in the early universe. Their brightness suggests an extremely dense packing of stars that no current model of star formation can explain. Stars form when gas clouds collapse under gravity, but the process is not instantaneous. It takes time for gas to cool, fragment, and collapse into individual stellar objects. The rate at which a gas cloud can convert itself into stars is limited by the physics of cooling, fragmentation, and radiation pressure. Blue monsters appear to have formed stars at rates that exceed these theoretical limits by large margins. Either the physics of star formation in the early universe was fundamentally different from what we observe today, or our understanding of that physics contains a serious flaw. The second category became known as little red dots. These are compact, dust-free sources observed during the cosmic dawn that weakly emit ultraviolet radiation while producing no detectable X-ray emission. Their properties are confusing to the point of being paradoxical. They suggest unexpectedly massive or evolved stellar systems despite existing at a time when the universe had barely begun producing stars. Some researchers proposed that little red dots might be supermassive black holes surrounded by stellar remnants, objects that should not exist so early in cosmic history because supermassive black holes were thought to require billions of years of growth through mergers and accretion. In January 2026, a breakthrough study from the Center for Astrophysics at Harvard offered a stunning alternative explanation. Using Webb data and sophisticated modeling, astronomers concluded that some little red dots might actually be enormous, short-lived stars. Not ordinary stars. Stars so massive that they dwarf anything in the modern universe, stars potentially powered by dark matter annihilation rather than conventional nuclear fusion. These hypothetical objects, called dark stars, had been proposed theoretically but never observed. If little red dots are indeed dark stars, they would represent a fundamentally new type of stellar object that existed only in the early universe, powered by a mechanism completely different from any star burning today. The dark star hypothesis is extraordinary and remains unconfirmed. But it emerged precisely because conventional explanations failed to account for the observed properties of little red dots. When standard physics cannot explain an observation, scientists must consider that either the observation is wrong or the physics is incomplete. Webb's observations have been checked and rechecked by multiple independent teams using different analysis methods. The data is too clean and too consistent across multiple observations to dismiss as calibration error or instrumental artifact. If the observations are correct, then something about our understanding of the early universe is incomplete. The third category of anomalous findings involves early supermassive black holes. These are objects that power quasars, the extraordinarily luminous cores of distant galaxies, by consuming surrounding gas and dust at prodigious rates. Supermassive black holes in the nearby universe contain millions or billions of times the mass of our Sun. Their origin remains one of the deepest unsolved problems in astrophysics. Standard models suggest they grew gradually over billions of years, starting from small seed black holes left behind by the deaths of the first massive stars, and growing through mergers and accretion over cosmic time. Webb has found evidence of actively accreting supermassive black holes at times so early in cosmic history that the standard growth model cannot account for their existence. There simply was not enough time for small seed black holes to grow to supermassive scales through known processes. The black holes appear to have arrived at their enormous masses far too quickly, suggesting either that the seeds were much larger than expected or that the growth process was far more efficient than models predict. In May 2026, another discovery compounded the mystery further. Astronomers using Webb observed a massive galaxy formed less than 2 billion years after the Big Bang that shows no rotation at all. This is profoundly strange. Galaxies form from rotating clouds of gas. The rotation is a fundamental property inherited from the angular momentum of the collapsing material. Young galaxies should spin. Old, evolved galaxies that have undergone many mergers may lose their rotation over billions of years as successive collisions cancel out the angular momentum. But finding a non-rotating galaxy this early in cosmic history implies that the processes that normally require billions of years to complete had somehow occurred within the first 2 billion years. The galaxy had aged far faster than physics should allow. Earlier in 2026, Webb discovered what researchers dubbed JWST's quintet, an ongoing merger of at least 5 galaxies occurring just 800 million years after the Big Bang. Standard models predicted that galaxy mergers at this early epoch should be simple affairs involving at most 2 or 3 small galaxies. Instead, Webb revealed a complex, multi-galaxy collision surrounded by a halo of oxygen-rich gas extending well beyond the galaxies themselves. The oxygen could only have been produced inside stars and subsequently expelled into intergalactic space through the violence of the merger. This demonstrated that galaxies were not only forming faster than expected but were interacting with and chemically enriching their environments far earlier than any model predicted. The cumulative weight of these discoveries has created a situation in cosmology that many researchers describe with terms normally reserved for moments of genuine scientific upheaval. The observations have produced what some call a crisis in early universe cosmology. Not because any single observation is inexplicable, but because the pattern of observations systematically points in the same direction. The early universe was more complex, more structured, more evolved, and more productive than the standard model predicts. Every new observation from Webb deepens this discrepancy rather than resolving it. Multiple explanations have been proposed. Some astrophysicists suggest that star formation in the early universe was significantly more efficient than models predict, allowing galaxies to mature faster. If the first gas clouds converted a larger fraction of their mass into stars per unit time, then massive galaxies could form more quickly. But this explanation requires changing the physics of star formation, which is constrained by observations of star-forming regions in the nearby universe. Others propose that dark matter interactions in the early universe catalyzed structure formation beyond what gravity alone could accomplish. If dark matter particles interact with each other through forces not yet detected, they might have clumped together faster, accelerating the formation of gravitational wells into which ordinary matter could fall and form galaxies. A smaller group of researchers argues that the findings challenge the standard cosmological timeline itself, potentially requiring adjustments to the cosmological constant or dark energy models. None of these explanations has achieved universal acceptance. Each one solves some problems while creating others. The dark star hypothesis, if confirmed, would rewrite the physics of the early universe but requires the existence of objects that have never been directly observed. The enhanced star formation hypothesis conflicts with observations of how stars form in the nearby universe. The modified dark matter hypothesis introduces new physics that has not been detected in any laboratory experiment. The adjusted cosmological constant hypothesis threatens to undermine a theoretical framework that has successfully explained decades of other observations. This is why the scientific community has been unusually measured in its public statements about Webb's discoveries. Scientists understand that the observations are real and that they challenge existing models. But they also understand that abandoning a theoretical framework that has passed every other test for 30 years requires overwhelming evidence and a viable alternative. Neither condition has been fully met. The evidence is strong but not yet conclusive. The alternatives are intriguing but not yet proven. The situation is genuinely uncertain, and honest scientists are reluctant to make definitive claims in a state of genuine uncertainty. But while the cosmological implications of Webb's impossible galaxies command the attention of theorists, the telescope's most emotionally resonant discovery involves something far closer to the fundamental question that drives public interest in space science. The question of whether life exists elsewhere in the universe. In 2023, Webb's instruments detected dimethyl sulfide in the atmosphere of an exoplanet called K2-18b, located approximately 120 light-years from Earth. Dimethyl sulfide, known as DMS, is a molecule that on Earth is produced almost exclusively by living organisms, primarily marine phytoplankton. It is not produced in significant quantities by any known geological or atmospheric process. The detection of DMS in the atmosphere of an alien world, even at marginal statistical significance, sent a shock through the astrobiology community. K2-18b is not an Earth-like planet. It is a Hycean world, a type of planet significantly larger than Earth with a mass of approximately 8.6 Earth masses. Theoretical models suggest it may possess a liquid water ocean beneath a thick hydrogen-rich atmosphere. Conditions on its surface, if it has a surface, would be profoundly different from anything on Earth. Any biology operating there would be fundamentally alien. The DMS detection sits at the 3 sigma confidence level, significant enough to warrant attention but below the 5 sigma threshold that physicists conventionally require for a formal claim of discovery. NASA's careful framing of the results reflected both the extraordinary implications and the genuine uncertainty. The agency explicitly stated that they were not claiming to have detected life on K2-18b. What they were saying was that they had detected a chemical signal that warranted urgent further investigation. Follow-up observations are ongoing. If the DMS signal is confirmed at higher statistical significance, the implications would be among the most consequential scientific announcements in human history. Not proof of life, but evidence. Strong, measurable, falsifiable evidence that biological chemistry is operating on a world orbiting another star. The distinction between proof and evidence matters enormously in science, but even evidence would transform the search for extraterrestrial life from a theoretical exercise into an empirical investigation with a specific target. Webb has also detected methane in the atmosphere of a Saturn-sized exoplanet called TOI 199b, a world with surprisingly Earth-like temperatures orbiting in a region between the scorching hot Jupiters and the frigid gas giants of our own solar system. This temperate giant planet represents a class of worlds that had previously been almost entirely uncharacterized because they are too faint and too far from their stars for earlier telescopes to study in detail. Webb's spectroscopic capabilities made the detection possible, opening a new category of worlds to atmospheric analysis. On another planet nearly 700 light-years from Earth, Webb discovered a bizarre daily weather cycle where mineral clouds appear every morning and vanish by nightfall. Rock clouds. Clouds made of vaporized minerals that condense in the cooler nightside atmosphere and evaporate when the planet rotates to face its star. This is weather unlike anything in our solar system, driven by temperatures hot enough to vaporize rock and atmospheric dynamics that redistribute heat across a tidally locked world. The observation demonstrates Webb's ability to characterize atmospheric processes on individual exoplanets with a level of detail that was impossible before its launch. Closer to home, Webb has studied planets and moons within our own solar system with unprecedented infrared sensitivity. It has observed the atmospheres of Jupiter and Saturn, detected previously unknown features in the rings of Uranus and Neptune, and studied the surface composition of objects in the Kuiper belt. It has provided the most detailed infrared observations of Mars ever obtained from space, complementing the data collected by surface rovers and orbiters. Each observation adds to our understanding of how planetary systems work, how atmospheres evolve, and how the conditions for life might arise on worlds very different from our own. But it is the impossible galaxies that keep cosmologists awake at night. Because if the early universe was genuinely more complex than models predict, the implications extend far beyond the specific question of how galaxies form. They touch on the foundations of our understanding of how the universe works. The lambda-CDM model is not merely a description of galaxy formation. It is a comprehensive framework that connects the physics of the Big Bang to the large-scale structure of the cosmos, the expansion rate of space, the abundance of chemical elements, the temperature of the cosmic microwave background, and the formation of everything we observe. If that framework needs modification to account for Webb's observations, the modifications could ripple through every branch of cosmology and potentially through fundamental physics itself. Some researchers have argued that the crisis may be less severe than it initially appeared. A study published in 2024 suggested that some of the apparently overmassive early galaxies might contain actively accreting black holes whose light makes the galaxies appear brighter and more massive than they actually are. When these little red dot objects are removed from the analysis, the remaining early galaxies are less dramatically in conflict with lambda-CDM predictions. The standard model may not be broken after all, merely stressed. But this resolution, if it holds, creates its own problems. If little red dots are powered by supermassive black holes, then the question becomes how those black holes grew so massive so quickly. The problem does not disappear. It shifts from galaxy formation to black hole formation, from one unsolved mystery to another. And the most recent observations from Webb in 2026 continue to find galaxies and structures that challenge the standard model even after the little red dot correction is applied. The scientific process is functioning exactly as it should. Webb is providing data. Theorists are proposing explanations. Observers are testing those explanations with new measurements. The cycle continues, each iteration bringing us closer to understanding what the early universe actually looked like and how it evolved into the cosmos we observe today. The resolution may come from a refinement of existing models rather than a revolution. Or it may require genuinely new physics. We do not yet know which outcome will prevail. What we do know is that the James Webb Space Telescope has revealed a universe stranger, more complex, and more surprising than anyone anticipated. Galaxies that should not exist. Black holes that grew too fast. Stars potentially powered by dark matter. Chemical signatures that might indicate biology on a distant world. Weather patterns involving rock clouds on alien planets. A galaxy that does not rotate when it should. 5 galaxies colliding when models said such events were impossible at that epoch. Each discovery opens questions that the next generation of observations may or may not answer. The telescope itself continues to operate flawlessly. Its instruments remain at peak sensitivity. Its orbit at the Sun-Earth L2 Lagrange point is stable. Its sun shield maintains the cryogenic temperatures necessary for infrared observations. Engineers estimate that Webb has enough fuel to continue operating for at least 20 years beyond its original 5-year mission specification. 20 years of observations that will continue to challenge, refine, or overturn our understanding of the cosmos. Webb was built to answer questions. Instead, it has generated questions that the entire field of cosmology is now struggling to address. The silence from NASA was not literal. It was the silence of scientists confronted with data that did not fit the story they had spent decades constructing. It was the silence of researchers who understood that speaking too soon, claiming too much, or dismissing too quickly would be a disservice to the scientific process. It was the silence of an institution that recognized it was standing at a genuine inflection point in human understanding of the universe. That inflection point remains unresolved. The data continues to arrive. The anomalies continue to accumulate. The models continue to strain under the weight of observations they were never designed to accommodate. And somewhere in the deep infrared glow captured by a gold-plated mirror floating 1.5 million kilometers from Earth, the answer to how the universe actually works may already be waiting. Hidden in the light of galaxies that should not exist, emitted by stars that burned and died billions of years before our sun was born, carrying information from an era when the cosmos was young, violent, and far more creative than anyone imagined. The James Webb Space Telescope did not find what we expected. It found something stranger. Something that made the most confident predictions of modern cosmology tremble. Something that may require us to rewrite our understanding of how the universe began, how it evolved, and what it ultimately is. That is what made NASA go silent. Not a single discovery, but a cascade of discoveries, each one more impossible than the last, each one pointing toward the same unsettling conclusion. We understood less than we thought. The universe is not what we expected. And the most powerful telescope ever built is only beginning to show us why. So here is my question for you in the comments. The James Webb Space Telescope has found galaxies that should not exist, black holes that grew too fast, and a possible chemical signature of life on a distant planet. Which of these discoveries do you find the most unsettling and why? Is it the possibility that our models of the universe are fundamentally wrong? Is it the chance that we might not be alone? Or is it something else entirely, the realization that after centuries of scientific progress, we are still standing at the edge of a mystery so deep that even our most powerful instruments can only scratch its surface? And here is a deeper question. If the standard model of cosmology needs to be revised, what does that say about the nature of scientific knowledge itself? Is it frightening or reassuring that our best theories are always subject to revision when new evidence arrives? Let me know your thoughts below. I am genuinely curious about your perspective. Let us discuss it together.